Hello guys, good morning. So today we'll be continuing our lesson on shear strength. So last time we talked about the shear contribution brought about by the concrete. So this time around we will be discussing the shear strength contribution due to the web reinforcement, or what is basically known or more commonly known as the stirrups. Okay. So there are four types of stirrups in general that we will be considering here in our uh, lecture. So the first one are the normal stirrups, or simply ties. Okay, so these are the common stirrups you see, which looks like this one. Okay, so these are normal stirrups. Sometimes we have what you call an open stirrup like this, or simply a straight tie. Okay, so we can make use of a straight tie like that. Okay, so these are known as basically the common stirrups and ties. So for the inclined stirrups, they are also the same as the stirrups and ties, but this time around, their position along the longitudinal axis is actually inclined. Okay, so if these stirrups are placed vertically on the beam, the inclined stirrups are normally placed in a uh, in an inclined manner like this one. Okay, so they are actually placed at an inclination. If this is the beam axis, so they are actually inclined in such a way as to prevent the crack from diagonally okay, crossing the stirrups. So these are normally called the inclined stirrups. We also have the bent up longitudinal bars. Okay, so these are actually the straight bars that we normally see in the drawing. So, but they are actually bent like this. Okay, so this is bent at the top and down at the bottom there. Okay, so these are both bent. And for the spirals, these are normally used on columns. Okay, but we can also use them in beams. Okay, so they are made up of spirally reinforced. Okay, so we can consider maybe longitudinal reinforcement, and then somewhere here are okay the spiral placed around. Okay, so the longitudinal axis of your reinforcement. Okay, so in this um, lecture, we are going to focus mainly on these stirrups and inclined stirrups, because these are the most commonly used for beams. So for the functions of the shear reinforcement, uh, as we have studied on your shear mechanism, so the shear reinforcement now carries a part of the shear. Okay, so we have a total shear which is equivalent to your concrete and your stirrups. Okay, and this concrete here happens to be divided into three mechanisms, which is the uncracked concrete, the aggregate interlock, and the dowel. Okay, action. So for the functions of the shear reinforcement, it carries a major part. Okay, so this stirrups carries a major part of your shear. Okay. It also adds integrity to the other shear mechanisms. So these are the other shear mechanisms, and it actually reinforces the efficacy of your shear mechanism. Excuse me. And number three, it also provides confinement to the concrete. So when the stirrups are placed all throughout the beam, confinement is improved. Okay, it is actually uh, uh, also helps in the shear mechanism aspect of your concrete contribution. Okay, so when you say confinement, the concrete is actually enclosed, no? It is enclosed with the stirrups and the longitudinal bars, so as to prevent. Okay, so what we are preventing here is the bursting of concrete. Okay, so when concrete cracks, there's a tendency for concrete to burst or to fall off. Okay, so it can go out of the cage. Okay, of your steel bars, and it will burst, and of course if some of the concrete bursted, the integrity of your beam will suffer. Okay, so in this figure now we can see an RC beam which undergoes shear cracking. Okay, so this is our shear flexural cracks, and the mechanism into which the shear, the stirrups, is actually undergoing is different from the mechanism into which your concrete uh, uh, part uh, contributes, is different from the stirrup contribution due to this mechanism. And the mechanism we are referring to is actually the truss mechanism. Okay, so this is a parallel chord truss analogy or mechanism that constitute your shear strength due to the stirrups. Okay, so if the stirrups are here, which are placed vertically like this, okay, so you can see that the cracks here are actually prevented from increasing in size, width, and number, okay, by the stirrups. Okay, and the vertical stirrup acts as your vertical members in a truss. Okay, so these are the vertical uh, web, okay, member, while the part here is actually the compression struts, the concrete compression struts, which of course is a part of the concrete mechanism, or the shear mechanism in the concrete. And while these longitudinal bars acts as your bottom chord. Okay, so this is now your bottom chord of the truss. These are the diagonal member web member. And this is the bottom chord of the truss. Of course, the top chord here will eventually be attributed to the presence of a compression reinforcement or a top bar reinforcement here. Okay, so this can contribute to the top chord of your truss, together with the concrete that has not cracked along this side. Okay, so there's still a part of concrete uh, that has not cracked at the top. Okay, so this is now your parallel chord truss mechanism, or simply the truss mechanism that will be the basis for our solution to the shear strength contribution. And if we take a look at the mechanism now here, okay, we can see here the crack angle. Okay, so this is alpha. Sorry, the crack angle, which is beta. And the stirrup angle, so if these are the inclined stirrup, assumed to be generally inclined. Okay, so if these are inclined stirrups, so you call this now your stirrup angle alpha. Okay, of course you have a tension force on the steel, and you also have a compression force on the uncracked concrete. Okay, so if you will see the free body diagram of the crack section, so it looks like this one. Okay, so this is now your uncracked concrete, and this is your AS. Of course, if there are tension bars here, or sorry, compression bars here, it will add to the compression strength of your mechanism here. Okay, so take note that the stirrup is inclined, so you have the stirrup tension TS, which is also inclined in this case. So to derive now your uh, formula for the stirrup, so we take a free body diagram of the bottom part of joint 1. Okay, so this is now your joint 1. So we have here a TS, a tension, we have the compression, okay, and then we have the vertical component of TS, and we have of course the tension here, which is of course not equal to the tension on the other side, so there's a differential tension on the other side of the bottom chord. And if we solve this free body diagram in terms of forces, by the way, your distance from this point to this point is defined by the height JD, which is the compression, the couple moment arm. Okay, so remember the definition of our moment capacity here, M. So we have simply your CJD, okay, or it's also equal to a TJD. So this JD defines now the distance from this point to this point 1 here, which is simply this vertical times the cotangent of the angle beta. Remember, this is the crack angle, okay, and this is the stirrup angle. So this is now JD cotangent alpha. So the distance from this point to this point is actually the spacing required for your stirrups. Okay, so if they are, because the next stirrup here will be inclined here, Okay, so this will be your TS, and the other stirrup will be placed somewhere here. Okay, so this is the mechanism. Okay, continuous mechanism. So this is now the S, the spacing required for your stirrup to prevent this crack, okay, to propagate from point 1 up to the top of your pier. Okay, so if we take a look at this free body diagram, we can now derive your Vs, which is simply Ts, the sine of alpha, or CD, the sine of beta. Okay, so if we want to solve Ts in terms of Vs, so we can say that Ts now is equal to Vs over sine alpha. And if more than one stirrup crosses one crack, then Ts is simply the resultant of all the stirrup forces crossing the crack. Okay, so let's say this crack has a lot of stirrups uh, crossing it, then your Ts is simply the total, or the resultant of all the stirrup forces which crosses your crack. And if we look into this formula now, uh, and divide this formula by the spacing on both sides. So if we divide this formula by S there and this formula by S here, we get this one. Okay, while S is actually JD cotangent alpha plus cotangent beta defined here. Okay, and TS is simply the area of the stirrup. Okay, so your V here signifies your shear. Okay, so the V there is a subscript for shear. So the area of the shear, or area of the stirrups, multiplied by the stress of the stirrup, or the stress in shear, is equal to your total tension force on the stirrup. Okay, so you substitute it there. Okay, so this is AVFB all over S. Okay, all over S is equal to Vs over sine alpha all over JD cotangent alpha plus cotangent beta. So this is now your working formula to solve for the spacing of the stirrup. And by proper manipulation, we can say now that the shear contributed by the stirrup at a spacing S is simply equal to AVFB JD cotangent alpha plus cotangent beta sine alpha. Okay, or if we assume JD to be equal to the depth D and alpha is vertical, okay, so the stirrup angle here 90 degrees means that your stirrup is vertical, and your crack angle, as we have assumed on our first discussion in the introduction, is 45 degrees. Then we can further reduce cotangent of 90. What's the cotangent of 90 degrees? Okay, so the tangent of an angle of 90 degrees is 1. Therefore, the cotangent of, the tangent of 90 degrees is actually uh, infinity. Okay, so cotangent of alpha is 1 over tangent of alpha. Okay, so this is now 1 over infinity is equal to 0. Okay, so this is now 0. Cotangent of 45 degrees is equivalent, let's change this into 90. Okay, so the cotangent of 45 is equivalent to the tangent of 45, which is equal to 1. Okay, and the sine of alpha, sine of 90 is also equal to 1. Okay, that's why we get now a value of Vs is equal to AV. This becomes the AVFBD all over S. So this is our working equation for the shear contribution of your stirrup. Okay, note that the FB is the yield strength of the web reinforcement, which is known as your stirrup. So for the code requirement, let's uh, have some important provisions in which we have to check this later for us to be able to ensure a safe design. So the minimum web reinforcement is given by this formula in SI. Okay, remember this is in SI. So you have a minimum stirrup, you cannot exceed, you cannot be lower than this one because this is the minimum code requirement. For letter B, the stirrup must be provided beyond the point where it is not theoretically required beyond VBC greater than VU. So I will explain this later on an example, okay, by way of giving you an example. So provide minimum shear reinforcement where VU is greater than 0.50 of VBC, and we have to have a maximum spacing on the basis of Vs. So Vs must be less than 1/3 of square root of f prime c bwd, or Vs greater than 1/3 of square root of f prime c bwd. So we have to satisfy both, okay, in case these are checked. Okay, so take note of these limitations. So these are limitations for BS. And also the maximum, this also includes another limitation for VS. Maximum VS should not exceed 2/3 of the square root of f prime c bwd to avoid over reinforcement in shear. Okay, so these are all in SI units. So take note of this. Okay, for the critical section for shear, we need to calculate the maximum shear on the basis of the critical section. So it means that we have to calculate shear at the point of critical, location. Okay, so these are the critical location for shear. So for simply supported, it is actually at a d distance from the bearing plate, okay, or simply the support. Okay, whatever is your support, it is at a d distance, the depth. Okay, what is d? D is the effective depth of the beam. Okay, so which means that the crack there will actually be crossed by the stirrup here. Okay, so the crack will not exist at the support itself, but rather at a d distance here. Okay, so the load here will be carried directly by the support. Okay, so there will be no expectation of crack, most probably at the point less than d distance. Also for continuous support, monolithic, so it's a d distance. For girder beam connection, it is exactly at the face of the support. Okay, so the abbreviation for this critical section is the FOS, face of support. And also for a girder beam connection where the slab is at the top, we have at the face of the support, because the crack may occur exactly here. Okay, also here, so it can crack somewhere here. So for loads located very near the support, where the location is within the d distance, a less than d, then your critical section is also at the face of the support. So you take note of FOS. Okay. This is also an FOS here. Okay, so we will be using those concepts and basic formula on my next video in reference to this example. Okay, so that's all for the first video class. I'll see you on the next video.